Hi everyone, I'm Josh Alman, and today I'm going to tell you about optimal degree polynomial approximations for exponentials and Gaussian kernel density estimation. And this is joint work with Amol Agarwal. So I want to tell you about polynomial approximations of real functions. And when you're talking about these approximations, there's two relevant parameters. So the first is b, which is a real number that measures how big the inputs to the function can be. And the second is delta, which measures our tolerance for error. So for a function f, we say how well you can approximate it by a polynomial is denoted by d sub b and delta of f, which is the minimum degree of a polynomial p such that for any input x between 0 and b, p and f differ by at most delta. So it's the minimum degree that you need to approximate it within delta on the whole range from 0 to b. So the case when b is a constant, like say b is 1, is really well studied in the math literature. Right? There's plenty of textbooks which describe almost like very precisely for almost any function you might be interested in exactly what kind of degree you need to approximate it to a particular error. But on the other hand, the case when b and 1 over delta are simultaneously growing is a lot less well understood. But interestingly, this is a case that arises a lot in computer science applications. So as you can imagine, and I'll give an example soon, in algorithmic applications, often both the magnitude of the input to the function and the tolerance for error can scale with the input size to the problem. So you really need to be dealing with both of them simultaneously growing. So in this work, we especially study the degrees needed to approximate exponential functions, e to the x and e to the minus x. And just because exponentials arise in so many places, we'll see these have a lot of different applications in computer science. So if you apply the typical framework from approximation theory, like from those textbooks I mentioned, it can get pretty close to calculating what these degrees are, but it loses often constant or even log factors. And as we'll see soon, even these seemingly small factors can be really important in some applications. So let me tell you our main result. So first for e to the minus x. So the prior work by Arekia and Sachdeva and Vishnoi, and also by Hochbrook and Lubitsch, bounded the degree to approximate e to the minus x between square root of b and this max of two terms. So square root of b log 1 over delta and just log 1 over delta. So our first main result is to tightly bound exactly what degree is needed to approximate e to the minus x. We show that it's exactly max of two terms. It's similar to the previous upper bound, so the first term is square root of b log 1 over delta before. The second term is a little bit less than the previous upper bound, so we improve it from log 1 over delta to include a new logarithmic term in the denominator. So we show that the previous upper bound was pretty close to tight. One thing that I think is interesting about this result is that you'll see there's a phase transition when b passes by log 1 over delta. So when b is larger, the degree has a square root dependence on both b and log 1 over delta. But when b is smaller, it gets just like a log dependence on b and a linear dependence on log 1 over delta. So this is an interesting phase transition, and as far as we know, transitions like this haven't been observed in polynomial approximation theory before. You really need to be studying how b and delta scale simultaneously to see a phenomenon like this. But interestingly, we'll see that this phase transition actually has algorithmic interpretations. So I'll show you a problem soon where when the parameters are on one side of this transition, you're able to solve the problem really efficiently. And when you move to the other side of the transition, there's provably, assuming some conjecture, no fast algorithm for solving the problem. And in fact, in addition to showing that this is the degree you need, we even compute the leading constant of the degree you need in almost every parameter regime. So here it is. For the purpose of understanding this talk, these details are not important at all, but you can see there are different cases depending on how b compares to delta, and in each one, we not only bound asymptotically what the degree is, but even what the leading constant in the degree is. And we'll see soon, there are some algorithmic applications where this degree appears in the exponent of the input size in the running time. And so even bounding this constant can be important for figuring out how fast your algorithm is. So that's our result for e to the minus x. And we similarly get results for e to the x. So prior work gave a somewhat loose bound on the degree, and we prove a tight bound that the degree is exactly this max of 2 terms. It's actually the same as for e to the minus x, except the first term is b instead of square root of b log 1 over delta. And again, actually we compute the leading constant exactly in all of the parameter regimes for e to the x. So these are our main results. So for the rest of the talk, I have 2 main goals. The first one is that I want to tell you about algorithmic applications of these degree computations, of these approximating polynomials for e to the x and e to the minus x. And I'm especially going to focus on a particular problem called the Gaussian kernel density estimation problem. Then my second goal, so the second part of the rest of the talk, will be about proof ideas for how it is that we computed these degrees so precisely. Okay, so let me start with the algorithmic applications. So just as I mentioned, just because exponentials appear in a lot of different places, polynomial approximations with low error for these functions have a lot of applications. So Arechia, Sachdeva, and Vishnoi, they were studying these in the context of a graph theory problem, finding balanced separators in graphs. But they also appear naturally in other cases. A really nice example is in approximating matrix exponentials. So when you want to do computations involving e to the power of a matrix A, there are methods we've known for over 60 years where you approximate this by using a polynomial approximation of e to the x, and then work with polynomials in matrices instead. Another place where these come up is in estimating the softmax function, which arises in a lot of classification tasks. They also come up a lot in kernel methods, which I want to tell you an example of now. So I want to tell you about the batch Gaussian kernel density estimation problem. In this problem, you're given as input 2 endpoints, which are vectors of dimension m, or you can think for now of m as order log n. And let's say we have a bound on how far apart these points can be. So we know the square of their diameter is at most b. So for every pair of them, their distance squared is at most b. So we're given these 2 endpoints. We're also given a vector w of length n, and we're given an error parameter delta. So in terms of these points, you should implicitly define the Gaussian kernel matrix. So it's an n by n matrix whose ijth entry is e to the power of minus the distance between I and xi and yj squared. So this is the Gaussian kernel, if you've heard of this before, evaluated at xi and yj. So you define this n by n matrix, and then the goal is to approximately compute this matrix times the input vector w. So more precisely, let's say we want to output a vector v such that its L infinity norm from the real k times w is at most delta times the L1 norm of w. Okay. So this is a problem, if you haven't seen it before, that arises in a lot of statistics and learning tasks. The idea is you can use it to estimate the probability density function of a random variable, which is a useful subroutine for a lot of different things. So the straightforward algorithm for solving it runs in about n squared time. You basically make this n by n matrix k in n squared time, and then you multiply it by the vector in n squared time. But the question we ask is, when can it be solved faster? So if you actually do create this n by n matrix k, it'll require n squared time just because it has n squared entries. But the reason I emphasize that we're implicitly defining this matrix is that you can imagine other algorithms that are able to approximate this answer without explicitly writing down all the entries of the matrix k. And indeed, the input size here is just like n log n for these n input points. So you could hope for a much faster algorithm. So as promised, you can solve this by using approximate polynomials. Here in the blue box, I'm just reminding you what the problem statement is. So here's the idea. Let's let p be the polynomial that delta approximates e to the minus x on the range from 0 to b. Okay, the polynomial we've been talking about. And let's define a new n by n matrix k tilde like this. Its ijth entry is the polynomial evaluated at the distance squared between xi and yj. So if the polynomial were exactly computing e to the minus x, k tilde would equal k. but because it's only approximating, k tilde is approximately equal to k. But one thing you can verify is that it now suffices to output k tilde times w instead of k times w, and it'll have the desired approximation guarantees. Why is this a good idea? The idea is that if the degree d of this polynomial is small, then k tilde has low rank, and you can compute k tilde times w a lot more quickly than you could compute k times w. So let me sketch the details of this. So first of all, we can write out what p evaluated at the distance squared means. It's exactly this. The distance squared between 2 points is actually this nice degree 2 polynomial. So in particular, this is a polynomial in 2m variables, like the mx variables and the my variables, and of degree 2d, because p has degree d, and we're plugging a degree 2 polynomial into it. So when you expand this out, it's a simple combinatorial argument that this has 2d plus 2m choose 2d monomials. I'm going to call this r. So it has r monomials given by this binomial coefficient. And in particular, a nice fact that's used a lot in the polynomial method is that k tilde has rank at most r as well. If you haven't seen this before, you can convince yourself that if p had just a single monomial, then the matrix would have rank 1. And then that means that since k tilde is a sum of r different rank 1 matrices, it has rank at most r. So using this, we can write k tilde as the product of A times B transpose, where A and B are both n by r matrices. And then to multiply k tilde times W, you can first multiply B transpose times W and then A times that. And both of those multiplications take just n times r time. So when r is smaller than n, this is faster than n squared time. Okay, so here's just what I said before. We can solve this problem in n times r time, where r is this binomial coefficient. So what is d? D is the degree to approximate e to the minus x that we talked about before. So it's we computed in our main result so that it's the maximum of these two quantities. What about the other parameters? Well, like I mentioned before, let's suppose m is like order log n. This is actually a reasonable assumption because in a lot of settings you can use dimensionality reduction techniques to get to that without loss of generality. For the error, let's pick the natural setting when 1 over delta is like polynomial on n. And in fact, this is an interesting setting because the prior best algorithm by Charikar and Simonlakis was only able to achieve like near linear time for solving this problem when 1 over delta was like n to the little o of 1. So they used a really interesting different technique based on locality sensitive hashing. But prior to this work, it wasn't known how to solve this problem in n to the 1 plus little o of time in like any parameter regime when delta is so small. Okay, so it turns out then that the running time you get depends on how big b is, the square diameter of the point set. So if b is little o of log n, then you can compute that we're in this second case of the maximum, and the degree is like log n divided by some super constant denominator. And so the degree is actually small o of log n. It follows that r is n to the little o of 1, and you actually get running time n to the 1 plus little o of 1. So we get a new near linear running time in a new parameter regime. And interestingly, this really did have to use our new improved degree upper bound. So we used the fact that we were able to improve the upper bound with this denominator, because without it, the degree would have been theta of log n, and we wouldn't have gotten such a fast running time. So what if b is bigger than this? Well, if b is little omega, so strictly bigger than log n, then first of all, our degree we calculate ends up being also little omega of log n, and r, the binomial coefficient, ends up being super polynomial, and we don't get anything nice from our approach. But in fact, we show, following the ideas of Backers, Indyk, and Schmidt, that assuming strong ETH, in fact, it's just impossible to solve this problem in truly subquadratic time in this parameter regime. So not only can the polynomial method not beat n squared time, but in fact, assuming strong ETH, it's impossible to beat n squared time in this regime. Okay, so what about in the middle? Well, when b is a constant times log n, then you can compute up here that the degree is also some constant times log n, and so the r, the binomial coefficient, is also n to the power of some constant, where the constant is some function phi of kappa, like the constant in B. So you get a running time that's like n to the 1 plus phi of kappa. So what is this? Well, we're able to compute using our bound on the degree that phi of kappa is at most order log 1 over kappa over log 1 over kappa. So we get a nice bound on the running time in this parameter regime. And interestingly, this computation uses not only like the asymptotic computation of the degree for approximating e to the minus x, but even though we had to use the leading constant to compute this. So as you can imagine, if you scaled up the constant by a factor of 100, then it would multiply these constants in the binomial coefficient by a factor of 100, and phi could get quite a bit larger. So actually understanding the running time in this middle regime requires you to, just because like the constant ends up appearing in the exponent of the running time in this phi of k at the end, understanding the running time you get requires understanding the constant in the degree to approximate e to the minus x. Okay, so that's the Gaussian kernel density estimation problem. And for the rest of the talk, I want to return to telling you about how it is that we proved these degree upper and lower bounds for computing e to the x and e to the minus x. So the real hero of this paper, the key technical tool we use, is the Chebyshev polynomial. So for any non-negative integer d, there's a Chebyshev polynomial q sub d of degree d. It's a single variable polynomial. It has a lot of equivalent definitions. One nice one is this trigonometric definition that for any angle theta between 0 and 2 pi, you want q sub d evaluate at the cosine of theta to be a rescaled version of the cosine of d times theta. So if you remember your trigonometric identities from high school, you can deduce that there is a polynomial that satisfies this trig identity, and that polynomial is the Chebyshev polynomial. But if you're not convinced that this is a polynomial, there's other equivalent definitions that make it more clear. Like you can define it recursively by the first polynomial is 1, the second polynomial is x, and afterwards you get this recursion where each one is a polynomial on the previous two, and therefore also a polynomial. Okay, so here's a picture of what the 10th Chebyshev polynomial rescaled a little bit looks like. You can see that, between -1 and 1, this trigonometric definition is kicking in, and it oscillates back and forth kind of like a cosine. But then outside of that range, the trigonometric definition is no longer, impacting what it looks like, and it blows up very quickly off to the sides. Okay, so one really nice property, really nice thing about Chebyshev polynomials is that they have very nice extremal properties. So here's one particular one we'll use. So among all polynomials p that have degree d and that are bounded between -1 and 1, so that the maximum value over all x between -1 and 1 of the magnitude of p of x is at most 2 to the 1 minus d, which is in particular the maximum magnitude of the Chebyshev polynomial on that interval. So among all polynomials with the same maximum magnitude as Chebyshev between -1 and 1, the Chebyshev polynomial maximizes the value of the polynomial evaluated at every point outside that interval. So for here in the picture, you can see between -1 and 1, our rescaled Chebyshev polynomial is always bounded between -1 and 1. But at any point, even a little bit to the right of it, like this green point over here, the Chebyshev polynomial is as big as possible, given that it was constrained to be inside that red box. And using this fact, we can already get a lower bound on the degree of approximating e to the minus x. So here's a graph of e to the minus x. And one thing we can see is if we had a polynomial that was approximating it, well, first of all, it would have to be bounded in this red box over here, because if it got outside this box, that would mean it was too big or too small, and it was more than delta away from the function on this interval on the right side. And then similarly on the left side, it has to get to at least this green point when you're evaluating at 0, because it has to be within delta of 1 when you're evaluating at 0. So any polynomial that approximates e to the minus x on this interval would have to stay within this red box here and achieve this green point, at least this green point here. So we know we can calculate that the minimum degree of a rescaled Chebyshev polynomial that satisfies these two constraints is square root of b times log 1 over delta. And the extremal property said that a rescaled Chebyshev polynomial has the minimum degree of any polynomial that satisfies these two constraints. So that implies that the degree for approximating e to the minus x has to be at least square root of b log 1 over delta. So this approach often gives a very good bound, but in most parameter settings, it actually loses constant or even super constant factors, and we need to be a little bit more careful. The idea is that, at the end of the day, the best polynomial is not just a Chebyshev polynomial, and by thinking about it that way, you're losing something. But it turns out that Chebyshev polynomials are nonetheless very important to approximating e to the minus x. So how would you approximate e to the minus x with polynomials? The first idea you might have is to truncate the Taylor series. So you can write e to the minus x as a Taylor series like this. And if you take just the terms of degree at most d, this gives a pretty decent degree d approximation to the function. But it turns out there's a better thing you can do, which is to instead truncate the Chebyshev series. So if you take the Taylor series, you can do a change of basis to write e to the minus x as a sum of coefficients times Chebyshev polynomials instead of coefficients times just monomials. And you can take this series instead and truncate it to only the terms of degree at most d. And it turns out this works better than truncating the Taylor series. So here's an example of approximating e to the minus x on the interval from 0 to 1 with degree 4. So here's how well the Taylor expansion does. So I've given a graph of the degree 4 Taylor truncation of this function minus e to the minus x. So this is a graph of how far away the Taylor truncation is from e to the minus x. And you can see it does a pretty good job. It approximates it to like 0.005. But if I do the same thing for the Chebyshev polynomial, the Chebyshev expansion, it actually does even better. So the Taylor expansion gets error about 0.005, but the Chebyshev expansion gets down to error like 0.001. And maybe the intuition here is that sort of, to the right of the y-axis, the Taylor expansion's error is always positive, always above the x-axis, as the Chebyshev expansion sort of wiggles back and forth and is allowed to take advantage of this a little bit. But let me prove more formally, though, that Chebyshev expansion truncations work really well. So here's the idea. So let's say f is our function, and on -1 to 1, it has this Chebyshev series, where I've just, again, rescaled by this 2 to the j minus 1 factor. So let's let p of x be the best degree d approximation for f on this interval. Okay, so here's the function with its Chebyshev series, and p is the best polynomial approximation of degree d. Then there's a nice upper and lower bound for how well this polynomial approximates f in terms of the coefficients of the Chebyshev series. So we show it's upper bounded by the sum of the magnitudes of the coefficients of degree bigger than d, and it's lower bounded by a similar sum of the coefficients squared divided by the degree, and then the square root of all of that. So the upper bound is not so hard to prove. It just uses the fact that 2 to the j minus 1 times the Chebyshev polynomial is always just between -1 and 1. The lower bound is a little bit trickier and involves some type of L2 argument. But in particular, if the a sub j coefficients decay quickly, so they get smaller and smaller very quickly, then basically the first term of each of these sums is important, and this gives a pretty tight bound on how well this polynomial approximates the function. It's between this coefficient and just 1 over square root of d times the coefficient. So in order to get a good bound on the degree of approximation, it suffices to compute these coefficients and figure out how quickly they're decaying. And that's what we do in the paper. We're able to prove that, for example, for e to the minus x, the coefficients look roughly like this. Again, the details are not so important here, but well, first of all, I should say, actually computing this is really the bulk of the technical work of our paper. It's not so easy, and there's a lot of different phenomena that are going on, you can see that this is like a sum of a few different terms, which in turn have sums inside of them. So depending on the relative scales of the different parameters of the problem, different terms are dominating the rest, and a lot of different things can happen, which is why there's different cases in our main result, and a phase transition happens depending on how big they are relative to each other. In fact, from this expression, it's not even so clear that this is decaying, but in fact, it follows from this middle term where you can see that as j gets big, it turns out to a log of something that's getting close to 0, so this middle term becomes a big negative term. But our main result follows by computing this and then analyzing and showing that they really do decay quickly. Okay, thank you.